Hey, I hope you're enjoying the algebra journey. We're back with these families again, and I hope you've got a few of these from the TINK program. And what we're going to do here is try to analyse the families of numbers here using the same idea as what we do in families of humans: surname, first name and generation. This is where we left it in the last presentation. So let's have a look at the surname here of this particular family. What have we got? Multiplying by 2 and then subtracting 3. So the surname might be multiply by 2, subtract 3. That's the thing that all the members here have got in common. The things that are the same and the things that are different are what we want to look at. And then let's do the generation next, because we saw that TINK generated family members by thinking of different numbers. So this would be the generation. What number TINK thought of? That ended up generating family members, and so these would be the family members, the actual value TINK got. So this would be the first name or the particular family member. So the generation and first name are different, but we have here a surname, a way of getting or generating this family would be the same. So I want you to do some work with these families, just what the heading of this video says. So come on down and I want you to have a look at some little ones here, again from the Harradine and Lupton booklet, and we've got this on video now. So I want you to pause the presentation and have a go at answering the questions A, B, C, D and E, and I'm going to come back and show you the answers in a minute. So let's pause it there and see how you go. Okay, so how did you go? I'm suggesting the surname for this family might be multiply by 5 and take 2, because these are the things that we did to generate the family, which were all the same. And what generation is the individual whose first name is neg 32? Here it is here. So the generation, the number we had to do the operations on to get neg 32 was neg 6. Who is generation 12? Okay, so generation 12, we better put 12 times 5, take 2. Do you get the idea? 60 take 2 is 58. Who is generation 2? Here's generation 2 is 8. Okay, so we could generate family members using the same sort of surname, the same operations. Oh, what about this last one? Supposing we can only have integer generations, is 57 a member of the family? Did you say no? Well, let's see if we can work it out. So after timesing by 5 and taking 2, you got the number 57. So here, if you added 2, you'd be back to timesing 5, which would have been 59. Okay, going backwards, and dividing by 5, 59 over 5 is 11/4. So that won't do as an integer or whole number generation. Now, if you did this course starting with algebra, what's that? You would know by now we could have put it like this. And what's been done? 2x has been times by 5. 2's been taken away, so reverse it. Add 2 to both sides and then divide by 5. And you don't get a whole number for the number TINK was thinking of. So that was the generation, wasn't it? This one here, that's generations in there. And they've all got to be whole numbers, according to this part E question here. So how did you go? Think about that. Let's go on. Let's do another one. And there's a few here to get your skill level up. Consider this family now. And I want you to pause the presentation and go through the 6 parts there. Or is it 7 parts? And see what you think. Okay, pause it now. Okay, how did you go? Here we go. I'm going to give you some answers now. So suggest a surname. All members have the same operations being done to the tink number, timesing by 6 and adding 5. Do you get it? Here it is over here. All are times by 6. Then everyone had 5 added. So completing the table, let's go down. Here's the first entry that was missing. 6 times 5 plus 5. Read it here. 6 times 5 is 30 plus 5, 35. And then the next one, 6 times 11, 66 plus 5, 71. 6 times neg 7, neg 42 plus 5 is neg 37. I think that one was already there. Then 6 by 1 plus is 6 plus 5 is 11. So I think there were only 3 entries. That one was already there. Okay, so to get the idea of generating family members by different generation numbers using the same surname here. Okay, the same operation. What generation is the individual with the first name 53? Here's the individual 53 and here's the generation number. So it's 8. Who is generation 12? Well, there's no 12s over here. Let's work it out. If 12 was a generation, you times by 6, 72 plus 5 is 77. Who is generation 2? There you are. Generation 2 was 17. Okay. Supposing we can only have integer generations, there's 59 a member. So in other words, the number tink thought of, times it by 6, add 5, and you've got to get 59. So here I put it over on the side. The tink number was times by 6 and 5 was added. So let's go in reverse now. Go backwards. I'll just rewrite that. That's a little bit untidy. We multiply by 6, added 5. Go in reverse. Take 5, you'd be back at 54 before the 5 was added. Then dividing by 6, doing the opposite, x is 9. So the generation number is 9. So yes, it's a whole number, so yes, we can. The answer to this question is yes, we can have that. Note that 53 is a member of the family and also the family from an earlier question. How does 53 differ? Well, 53 is in a different generation. You need a different tink number to work on to get the same first name, the same family member. Okay, you're starting to get the hang of this, spotting things that are the same and things that are different amongst family members. Come on down, let's do a bit more. Here we are. Find 2 families to which 28 belongs and within which it is the same generation. Okay, I want you to pause the presentation now and have a go. All right, coming back, I've got to get the family member to equal 28. So let's think about timesing something by 4. 4 times what? 5 is 20. Add 8 would give 28. So my first family would be timesing by 5 and adding... let's do it differently. Let's call this the generation number. So I'm timesing by 4 and adding 8 is my family. Now I've got to work out another family using the same generation. So I've still got to use this same generation here. So let's do 6 times 5 is 30. Take 2 would be 28. There's an infinite number of these, isn't there? So this family would be called multiplying by 6 and taking 2. And we've got a generation number here which is common. Using 5 in both of those families, you generate the same individual. Okay, using the same generation number, but 2 different families. So there's an interesting variation. Okay, so think about this, of how different ways of generating families of numbers. All right, come down. We're going to use some correct mathematical terms now. And I think you saw some of that in Algebra. What's that? The first presentation in this series. So, let's have a look at this table. What are things in common down here? First of all, multiplying by 5. Here's all the 5s here. And subtraction of 2. Here's all the 2s being taken away. Things that are different. the number being multiplied by 5, and we call that the generation, and the result, or the number that Tink gets, the family member, the individual family member. So these differed, and the family members we produced differed. Different first names there. Okay, so here we are. The surname is 5 times some number, subtract 2. So I was calling it times by 5, take 2. And we could call it, using x here, 5 times a variable number, because as Tink thought of a different number, x changed, and take 2. And we generally use the times, leave the times out here, as we saw in the first presentation, algebra. What's that? Okay, so let's start building up the proper terminology in Mathland. We don't usually, in mathematics, use surnames and so on. We have a different jargon, if you like. So come down now, and let's have a look. So here's the first bit of that. So I want you to get your notebook out and title it Algebra. More notes on algebra. And what I want you to do is to copy this down. So pause the presentation and have a go there. When a letter takes the place of many different numbers, it's called a pronumeral. Pro meaning standing for. Pronumerals are normally presented in italic font, okay, to show that they are standing for numbers. A pronumeral may represent a physical quantity or simply just a number. We've just been seeing numbers for the moment. Letter shows that a pronumeral is often x, but can be anything you use your likes, like n for number maybe, or for h for height. And in some cases, and we see this later, 2 or more different pronumerals may be required. Okay, can you write that down please and think about whether you agree with it and discuss it with your classmates and your teacher. Okay, let's go on now. A branch of mathematics that deals with the study and use of pronumerals is called algebra. That's why we headed this up with algebra, that title. Let's go on a bit further now. Here's the next point. When a pronumeral is written next to a number, like 5x, it means 5 times x. Just mathematicians being lazy. I don't think I agree with Mr. Harrison on that. It's just a neater language, isn't it? This is neater. A neater way of writing that. So our language wants to be neat and concise. All right, keep going down here. A collection of numbers, operations and pronumerals like 5x take 2 is called an algebraic expression. And back in that first presentation, algebra, what's that? We were writing mathematical sentences. So we had algebraic expressions but equal to something, or an equation. We're going to come on that later on. And this algebraic expression is called the surname of the family. And every family member can be generated by putting in different values of x, and you get a different member of the family. That's why x was called the generation number. And it could vary. Many, many values. How many values, I wonder? Many, many values. Would we put a restriction on that? We'll have a think about that and we'll come back. Come down here and let's keep developing the idea. Oh, here we are. Have many values, family members. We learned the last second we think of this as the first name of the family member. So as you put in more x's, x values are going to generate more family members. The family member is the final number that you get when you put x as a generation number and do things to it. Like 5 times x take 2 would produce, many, many family members. All right, come down and answer this question then. There's something for discussion here. Can you see how the expression like 5x take 2 captures all members of the family? If not, discuss this with others. How would you answer that? Okay, pause the presentation and have a bit of a discussion. Coming back, captures all of the members of the family. Yes, because you could put an infinite number of possibilities in here. An infinite number of x values, having a huge family. And back earlier, we had that x had to be an integer, a whole number. We put that restriction on the family. Okay? But it doesn't have to be. If it could be any real number. Okay? Fractions, decimals, square roots, all sorts of things. So we can, in fact, capture all members of the family by changing that generation number and get a huge family. All right, and later on we're going to see what that family, again, has something extra in common. And we'll explore that later on. All right, come on down now, and more practice for you. The idea here, you're trying to do these exercises without the use of a calculator. All right, so let's have a go now, and I'll just bring this up a little bit here, and see how you go doing this without a calculator. All right, I want you to pause the presentation now and have a go. There's about 8 parts there, I think. So see how you go. I've been busy here. Here's some answers for you. So write down an algebraic expression. What do they have in common? Timesing by 5 and subtracting 4. So we want an algebraic expression this time. So we're going to put an x in. 5x take 4. Or 5n take 4 if you like. Find the value of the expression when the pronumeral takes the value 7. So stick 7 in there. Give you 31. Stick 9 in there. 41. Stick neg 12. Watch this one. 5 times neg 12 is neg 60. Take 4 is neg 64. Further down the left of the number line there. When the algebraic expression has 19, so you're starting off saying we know it's 19. So the missing letter has been times by 5 and 4 has been taken away. Let's reverse that. Let's add 4 and then divide by 5 and get 23 over 4 or 5 3/4. When the algebraic expression is 54, do the same thing. Add 4 is, I think that's not right. 54 and 4 is 58. Just change that. So here we go, 58, that's 58 over 5, 11 and 3/5 there. Okay, so you're doing the opposite operations, aren't you, in reverse order, sort of unpacking a present, going back to see what's in there. So here, when the value is 25, so you're adding 4 to get 29 and dividing by 5. So check that out there and make sure you got those. Now, how many members are in this family? Well, you could go on for an infinite number, couldn't you? Let's come up the top here. Look in here. You could actually put an infinite number of possibilities there. They don't all have to be whole numbers. They could be fractions as well. So on and on you could go. A huge family there. All right, just notice over here a little bit of notation. That implies sign. That's what we use to make our language lead on from one line to another. And it's the word implies. It's saying, if we make this statement, it suggests or implies that that was true, and that implies that. It's like punctuation in English, if you like, or any language. Okay, so you might try to dress your solutions up, your reasoning there, and to make it look a little bit more mathematical. All right, come down now and let's have a look at another one. Okay, we'll just go a little bit lower here. Okay, so here's our family. We've got a couple. Okay, so here's our family, algebraic expression, etc. Same thing again. So I want you to pause the presentation and have a go. Okay, how did you go? Here we go. Write down the algebraic expression. What's in common? Been times by 9 and 7's been added. So we're going to say 9 times our number, our generation number, plus 7. So the pronumeral is going to take the value of 14. So put 14 in here. This is a bit hard without a calculator. But you could take 10 lots of 14s, 140, minus 1 lot of 14, is 126 and plus 7 is 133. So there's a bit of a trick you could do there. Or 9 times 14 is 9 lots of 10 plus 9 lots of 4 is 90 plus 36, 126. So you can get by without a calculator here. Okay, what about when the pronumeral takes a value 7? 9 times 7 is 63 and 7 is 70. What about when it's 9 lots of neg 15? 9 lots of 10 is 90 and 9 lots of 5 is 45. 90 and 45 is 135, but it's all negative. So it's negative 135 plus 7 is negative 128. Remember, you're coming 7 back from that negative side of the number line. Now, when the algebraic expression equals 115, so this equals 115, what's been done to x? See it there? Been times by 9 and 7 was added. So let's reverse it. Take 7, go back to 108, divide by 9 is 12. It'll work nicely. And when the value is 61, do the same thing. Take away 7, get 54. Divide by 9, get 6. And then when it's 26, same thing. Subtract the 7, get 19. Divide by 9, get 2 1/9. Okay. So how many members then? Well, you've got an infinite number of members. Because let's come up to the top here, up to this row, or column rather. That column, you could have any number in there, lots and lots of them. There'd be infinite number of members of this particular family. Okay, let's keep going now, and I want you to start looking at something a little bit different here. It'll be a little bit tricky here, and you might need a calculator for this one. Have a look up the top. Okay, so I want you to pause the presentation, study it carefully. There's extra pieces in here. Okay, you might have to be a little bit tricky with this. So pause it and have a go. Okay, here we are. Did you get it? Well, I'll just go up page a little bit so I can explain this to you. Can you see that there was a column here and a column here which had identical values? So maybe there were two numbers both having the same value and which we could have both called generation numbers or variables. Here, because those two rows, or columns, matched each other, you could call them x. And when this x was 3, this stayed with it. So that was consistent. So x would have done, because as you changed generation over here, this one changed as well. So I could have called them a common letter. Did you think of that? Let's develop that a bit. Find the value of the expression now when the pronumeral takes a value of 14. So 13 lots of 14 plus 7 plus 9 lots of 14, take 2. I do it for the next one. 13 times 7 plus 7 plus 9 times 7, take 2. Remember, at sped maths, you've got to do the multiplication first. Okay, again 159. 13 times neg 15 plus 7, 9 times neg 15, take 2, 325. Okay, do you get the idea here? Now, let's have a look. I wonder if you thought there's an easier, quicker way of doing that. It's going to come up here. Determine the value of the pronumeral when the expression is 115. 13x plus 7 plus 9x, take 2, 115. Did you think you could join the 7 and neg 2 together? Plus 7, take 2 is positive 5. And 13 lots of x and 9 lots of x, that surely is 22 lots of x. We might have seen that up here. Okay, or if x was items, 13 dogs plus 9 dogs is 22 dogs. And then we can divide by the 22 going back, and we get the answer 5. Did you think about that? So let's use that now. If we have a common x value in a problem, we'll just call it x, and we can collect up the number of them that we've got. 22x, and collect up the numbers as well. This is sometimes called collecting terms that are like each other. Little pieces of our expression that are like each other. And this time it comes to 61. So then subtracting 5, going back now, it would be 61 take 5, 56, then divide by 22. We've got one of those mixed numbers there now, 2 and 6/11ths. Cancel it down. What about this one, when it equals 26? Take away 5, you get 21, and you get the number 21 over 22 here. So there's some strange numbers we could have in Xland for that variable x. And we could restrict it to integers, but if we have all the possible numbers, there's going to be an infinite number of members of this family. You can keep generating members of this family over and over. All right, I hope you're getting the hang of it now. Come down, and we've got a few just to finish off with. Study the following number family. Write down an algebraic expression that describes each member of the family. These are each looking a little bit different from each other. So have a go, pause the presentation, and see what you come up with. Let's have a look now. We could say 9 take 4x. See, these are the same in each row, and we have different values here. And so our algebraic expression would be to let the things that are different be replaced by a pronumeral, so we can vary the values there. Okay, the things that are the same become our surname or crucial parts in there of our algebraic expression. All right, let's go down, let's do some more. Keep your wits about you here, they're getting a little bit harder. Okay, I want you to pause the presentation, study what is the same and what is different here. All right, come back now. Did you see that these two columns have matching values as you go down? So if we call this one x, every time you get that, you get the same value over here. So that we could use the same letter, because as it varies, both of these columns vary in the same way. So the algebraic expression would be 5 take 3 times x times x. And do you remember when you multiply a number by itself? 2 times 2 is called 2 squared. 3 times 3 is called 3 squared. So x times x, guess what? 3x squared. So hey, this little algebra system of representing families is quite neat and concise. It tells you what's going on up here in one simple algebraic expression. All right, how did you go? Come to the next one now. Getting a little bit harder. Think about this one now. Okay, pause the presentation and have a go. All right, let's have a look at it. What's the same and what's different? Here we are. These two columns are the same number, and the operations through here with the 2's and the 5 are the same, so that's going to be the surname. But these are varying, aren't they, as we go down? But they're varying with each other, so they could both be described by the same generation number, if you like. So let's have a look. It's 2 times x plus 5. And here it is 2x squared plus 5. X times x, a number times itself, is a square. How did you do? Thinking about things that are the same and things that are different. So just be careful here. These two columns were the same, but they varied, so that you meant we'll probably introduce something that will generate different values, and that's x there. All right, last one now. How are you going? Think about what you're doing here. Okay, study the following number family. Now study this one carefully, a little bit of difference coming on here. A couple more things that are varying. Okay, pause the presentation and have a go. All right, coming back. Do you notice that in each of the members they were generated by the same things here? The timesing by 2 and the adding 5. But oh, hang on, there's something going on here, mate. They were varying, but they weren't varying together. They're not the same here, but both are varying. What do you reckon you could do? Okay, well, we usually let something varying be x. So it's 2x times by, oh, there's something else varying. Oh, we could use y maybe. And then add 5. And we don't need the time sign we said before, so we could write 2xy plus 5. How about that? Do you get the idea here? We've got two columns that are both varying, so we have to introduce a pronumeral standing for that variable number, and we put a number in there. We can generate different family members, but we've actually got to specify two varying numbers there, an x and a y. How about that? Can you see how algebra is growing before your very eyes and could be very useful in analysing problems? All right, look, I hope you've enjoyed this, and there's more to come as we get into more interesting applications. So I hope to catch you in the next presentation. Cheers for now.